So the way that a railgun works is that you have two rails that run parallel to each other, and with these two rails, each of them have their own individual magnetic field. These two magnetic fields will then combine to create a larger magnetic field. So then you place a projectile in between these two rails, and this magnetic field will then drive the projectile out at a force. So the equation that we're going to use here is acceleration equals inductance times current squared over 2 mass. So inductance is equal to kilograms meters squared over seconds squared area squared, and its unit of measurement are henries. Alright, so we're going to be trying to accelerate an object of 500 kilograms, that's just random, to acceleration of 273.95 meters per second, which is the acceleration of the sun due to gravity. Also, we'll be using zero point 0.6 henries for this equation because that's optimal for a railgun, and we'll be solving for current. So here's our equation. As you can see, and that inevitably will equal 456,583.3 amps.
If we use Einstein's principle of equivalence, which is all physical experiments conducted in a uniform gravitational field and in an accelerated frame of reference give identical results, then we can conduct an experiment where an observer shines a flashlight towards the opposite wall of an elevator, which is in deep space and has zero acceleration. The light would strike the wall at its initial height. But if the same experiment is conducted with an accelerated elevator, the elevator is accelerating upward during the time that the light travels across the elevator. Thus, by the time the light reaches the far wall, it strikes at a lower level. In fact, the light has followed a parabolic path, just as one would expect for a ball that was projected horizontally. This phenomenon was discovered during an eclipse because the stars that would normally be behind the sun at that point could be seen like they were to either side of the sun. This effect is known as gravitational lensing. The waves of light coming from the star travel by the sun and are bent towards the observers on Earth because of the distortion in space-time of the sun. So what our group wanted to discern was if we were able to ever in the future observe this process on a smaller scale. So if light is affected by gravity, and so are projectiles, then the projectile equations could be used to try to solve for the distance traveled in the y direction. So here we have the distance in the x direction is 1 meter. The change in y is what we're trying to solve for. And so because we know that the gravity of the sun affects light and bends it, we used the acceleration due to gravity of the sun. And then we have the initial velocity in the x direction is the speed of light, and the acceleration in the x direction is 0. The initial velocity in the y direction is 0. And so first we need to solve for time. So time, we get dx over vi of x is 1.0 over 3.00 times 10 to the 8th, which is the inverse of c. And then once we get that, we can put it into this equation and get the change in the y. And so we get it VIY times t, since VIY is 0. That term is 0. And then 1/2 times the acceleration of the sun, the acceleration due to gravity of the sun, times the time squared is negative 2.03 times 10 to the negative 20th meter. And that is so insignificant that we can't detect it at all. So what we looked at next was if we could find the acceleration needed to change the distance in the y direction 1 nanometer. Because we are able to observe nanometers just
So we put the 1 nanometer in place of dy, and that equals 1/2 times the acceleration we were looking for, times the time it took for the light to hit the wall, and we got the acceleration needed would be 1.8 times 10 to the 8th meters per second squared. So really this effect of the gravitational bending of light can only be viewed over very long distances, like light years, because um, the speed of light is so substantial that we won't be able to um, make a change in such a short distance.
In this portion of the experiment, we will be studying the effect of light in space. What would happen if we were to turn on the headlight in space? First of all, it's important to establish how light works. Light works as a particle. For example, it has its constant, c, which is 3 times 10 to the 8th meters per second. It's important to note that light works as a particle. As you can see here, light moves from point A to point B. But when put through the cup, it's important to note that it goes through a different medium. It's not that the light is moving at a different speed, it's just that it works as a particle, and thus must move around the water particles in order to reach point A to point B. Thus, the speed is not different, rather the space to move is different, and thus it takes longer for it to reach point A to point B. But light itself is not moving quicker. So, a quick analogy is, imagine a person moving from point A to point B. If it's a clear hallway, then he'll be able to move quickly from point A to point B at a constant speed. But let's put a group of people in that hallway. As displayed here in this diagram, we can see that he still arrives from point A to point B, but there are people in his way. He will move at that same constant speed. However, since he has to weave around all those people, it'll take longer for him to travel that distance.